The universe is not a random collection of lights, but a single, connected structure. This hidden architecture, known as the cosmic web, is the largest thing that exists, and its map holds the key to our cosmic origins. By the end of this, you will understand how this invisible framework shapes everything, from the birth of the first stars to the ultimate journey of all matter. For centuries, its true form was a complete mystery, its delicate filaments impossible to see directly. How could something so vast remain hidden in plain sight? And what forces drew its first lines in the emptiness of space? What does it mean to discover that we live inside a web of cosmic proportions? These immense voids are not simply empty space. They are the negative spaces in the cosmic canvas, the silent counterpoints to the bustling galactic cities. Finding them was like looking at a map of the world and noticing for the first time the true scale of the oceans. The sheer size of these quiet regions presented a profound puzzle. How could the universe arrange matter into such extremes, with bustling superclusters of galaxies hanging like dew on a spider's web, and these vast, still deserts stretching between them? The answer would not be found by simply looking at the galaxies themselves. It required peering into the spaces between them to find the unseen threads that must be holding this entire structure together. This search would lead astronomers to the most dominant, yet most elusive component of our universe, a mysterious substance that forms the very framework of the cosmic web. This ghostly tissue, dark matter, is the universe's primary architect. It is an invisible substance that completely ignores light, making it impossible to see with any telescope. We cannot touch it, photograph it, or directly detect it, yet we know it is there because its immense gravitational pull dictates the motion of stars within galaxies and the very shape of the cosmos itself. Think of it as a cosmic scaffold, an unseen framework upon which everything visible is built. For every galaxy, star, and planet you can see, there is about 6 times more of this dark, unseen matter holding it all in place. Its story begins in the earliest moments of the universe with the faintest of whispers. In that primordial darkness, the distribution of dark matter was almost perfectly smooth, but not quite. Tiny, random ripples in its density existed, imperfections so small you could barely measure them. These minute fluctuations were the universe's first blueprints. Gravity got to work on these slight overdensities, patiently pulling more and more dark matter into them over billions of years. The slightly denser patches grew denser still, while the emptier regions became vast, hollow voids. This gravitational sculpting created a colossal web of dark matter filaments, a hidden lattice spanning the entire cosmos. Where these invisible threads intersected, the gravitational pull was strongest, creating deep wells that acted as cosmic traps. Ordinary matter, the gas and dust that would eventually form stars and planets, was helpless against this pull. It simply flowed along the gravitational contours laid down by the dark scaffold, pooling at the nodes and streaming along the filaments. The brilliant galaxies we see today are just the visible tracers, the glittering lights strung along this underlying dark matter architecture. To understand the cosmic web is to acknowledge this unseen cartographer, whose silent, gravitational hand drew the first map of everything. This blueprint for the entire cosmos has a name, the Lambda CDM Model. It is the most successful story we have for how our universe came to be, a precise recipe that combines the two greatest cosmic mysteries into a single, powerful theory. Lambda represents dark energy, the mysterious force causing the expansion of the universe to speed up. Cold dark matter is the other key ingredient, referring to the slow-moving, invisible particles that gravitationally clump together to form the cosmic scaffold. Together, these two components choreograph the grand ballet of cosmic structure. We can watch this dance unfold not through a telescope, but inside a supercomputer. The most famous of these digital universes is the Millennium Simulation, a monumental calculation that started with a nearly smooth, early universe and let the laws of physics run their course. Within this virtual cosmos, gravity acts on the cold dark matter, pulling it into an intricate network of filaments and halos. Over billions of simulated years, these halos merge and grow, tracing out the very same cosmic web that our telescopes now reveal. The stunning match between these simulated universes and our real observations is a profound confirmation. It tells us that our fundamental understanding, while incomplete, is pointing in the right direction. The true power of this model, however, lies in its predictions. It tells us exactly where to look in the real night sky to find the hidden architecture of our universe. To translate this blueprint into a real map, astronomers needed to find a way to see the invisible. Their first powerful tool was to trace the cosmic web using the only things we can directly observe, the galaxies themselves. This monumental effort began with galaxy redshift surveys. The concept hinges on a simple but profound fact. As the universe expands, it stretches the very fabric of space, and this stretching also lengthens the light waves traveling through it. We see this as a color shift toward the red end of the spectrum. The farther away a galaxy is, the faster it appears to be receding from us, and the more its light is redshifted. By carefully measuring this redshift for millions of galaxies, astronomers can calculate their distances, transforming a flat, two-dimensional star field into a rich, three-dimensional map of cosmic structure. Pioneering projects like the Sloan Digital Sky Survey dedicated enormous telescopes to this single task, systematically scanning the sky and cataloging the precise positions and redshifts of countless galaxies. The result was a revelation. When they plotted the locations of these galaxies in three-dimensional space, a pattern emerged from the apparent chaos. Instead of being scattered randomly, the galaxies aligned into vast, intersecting walls and long, delicate tendrils, wrapping around enormous, empty voids. It was like watching a connect-the-dots picture slowly materialize, where the final image was the hidden architecture of the entire observable universe. These surveys provided the first rough sketches of the cosmic web, transforming it from a compelling theory into a tangible, physical reality. They proved that we could indeed chart the largest structures in existence, one galaxy at a time. But these maps had a fundamental limitation. They only showed us where the luminous matter had gathered, the glittering nodes of the web. The filaments themselves, the dark threads connecting these brilliant cities, remained unseen, a subtle presence suggested by the pattern but not yet directly observed. So our first maps of the cosmos were fundamentally incomplete, tracing only the bright specks of light and leaving the true structure in shadow. This luminous matter, the stuff of stars and planets that scientists call baryonic, accounts for a mere fraction of the cosmic web's total mass. Relying on it alone is like trying to understand a vast modern city by only noting the position of every street lamp. You would see the glowing nodes, but the dark roads connecting them, the hidden power grids, and the immense, unlit buildings would remain a complete mystery. In our universe, the dark matter filaments and enormous reservoirs of diffuse, non-glowing gas form this hidden infrastructure, containing the overwhelming majority of all material. To make matters more complex, the placement of a bright galaxy does not always perfectly mark the heart of the dark matter scaffolding. Some dense knots of this invisible matter might host no bright galaxies at all. while brilliant galactic cities can sometimes be found in less dense regions, like a single, shining tower built away from the main downtown core. This inconsistent relationship meant that a map of the lights was not a true map of the mass. The quest to see the complete picture, to illuminate the dark roads and hidden framework of the cosmos, would require a much more subtle and ingenious approach. Astronomers needed to find a way to use the light itself to reveal the darkness. Einstein's theory gave us a way to see the invisible. He predicted that massive objects do not simply sit in space, they warp it, creating a kind of gravitational lens. When light from a distant galaxy travels toward us, its path is not perfectly straight. It bends as it passes through the distorted space around a massive foreground object, like a cluster of dark matter. This effect, called gravitational lensing, subtly distorts the shapes of those faraway galaxies, stretching them into faint, smeared arcs. At first, this was just a theoretical curiosity. But astronomers realized they could use this cosmic distortion as a measurement tool. If a single, distant galaxy appears slightly stretched, that could be its natural shape. But if you see thousands of galaxies all stretched in the same direction, their light all bending around the same patch of seemingly empty space, you have found something profound. You are looking at the gravitational footprint of an invisible mass. This is weak gravitational lensing, and it became our most powerful method for mapping the dark universe. By analyzing the subtle, coordinated warping of millions of background galaxies, supercomputers can work backward to calculate the exact location and density of the foreground mass that caused the distortion, whether that mass emits light or not. The resulting maps are breathtaking. They reveal the true cosmic web in its entirety, showing not just the bright knots of galaxy clusters, but the immense, dark matter filaments flowing between them like colossal rivers of shadow. For the first time, we could see the gravitational skeleton of the cosmos, confirming that the luminous galaxies we see are merely decorations on a framework built from something we cannot see. This technique opened a direct window into the hidden architecture, proving that the cosmic web was not just a beautiful idea, but a physical reality woven from dark matter. This fossilized light carries a message from the very beginning of everything. The cosmic microwave background is the oldest photograph we have of our universe, taken when it was a mere 380,000 years old. At that moment, the cosmos transformed from an opaque, searing fog of particles into a transparent expanse, releasing its first burst of clear light. That light has been traveling for over 13 billion years, cooled and stretched by the expanding universe into a faint microwave whisper that permeates all of space. It is the cosmic afterglow, and it holds the original blueprint. When we point our most sensitive telescopes at this background radiation, we do not see a perfectly uniform blanket. Instead, we detect incredibly subtle variations, tiny patches that are ever so slightly warmer or cooler than their surroundings. These minute temperature differences are not random. They are the gravitational footprints of the universe's first structures. A slightly warmer spot marks a region where matter was just a little more densely packed, a region where gravity had a slightly stronger grip. These were the seeds, the microscopic imperfections that would determine the fate of the cosmos. Everything we see today, every filament of the cosmic web and every vast void, was encoded in that primordial pattern. It is like looking at the fossilized imprint of a sapling and knowing that it would one day grow into a specific, sprawling oak tree with a unique arrangement of every branch and leaf. Cosmologists use these temperature maps as a starting point for the ultimate cosmic simulation. They feed the patterns from the cosmic microwave background into powerful computers and let the known laws of physics play forward through time. Gravity acts on those initial overdensities, amplifying them over billions of years. The dark matter begins to clump, drawing in the ordinary matter, and the faint ripples in the ancient light slowly evolve into the grand design of the cosmic web. The stunning agreement between these predictions and the large-scale structure we observe today is one of the strongest validations of our entire cosmological story. This ancient echo does not just tell us where we came from. Its precise details also reveal the fundamental ingredients of the universe, the exact amounts of dark matter and dark energy that were necessary to sculpt the world we see around us. It is our most direct link to the moment of creation, a silent witness that has watched the entire cosmic story unfold. But the dark matter scaffolding is not entirely empty. Stretching along its invisible filaments is an ocean of primordial gas, a diffuse and searingly hot hydrogen plasma known as the intergalactic medium. This is the universe's hidden reservoir of normal matter, the stuff you and I are made of, but it exists in a form so tenuous it is almost a perfect vacuum. For a long time, these gaseous rivers remained completely invisible to our telescopes, their faint glow drowned out by the brilliant light of galaxies. To find them, astronomers had to become cosmic detectives, using the brightest lights in the universe as their flashlights. They turned to quasars, the incredibly luminous cores of distant galaxies, powered by material falling into supermassive black holes. A quasar acts like a cosmic beacon, its intense beam of light traveling for billions of years across the universe to reach our telescopes. As this light journeys through space, it passes through the delicate filaments of the cosmic web. The diffuse hydrogen gas within these filaments does not emit its own light, but it leaves a distinct fingerprint by absorbing very specific colors from the quasar's brilliant white light. When astronomers break this distant light into a rainbow-like spectrum, they do not see a clean, continuous band of color. Instead, they find it is sliced by thousands of dark absorption lines, a dense thicket of missing light known as the Lyman alpha forest. Each one of these lines is a direct measurement. It tells us that the quasar's light has passed through a specific cloud or filament of hydrogen gas at a precise distance. It is like analyzing the beam of a searchlight after it has passed through a dense, patchy fog. By studying the precise pattern and depth of these absorption lines, scientists can perform a kind of cosmic tomography. They can reconstruct the density, temperature, and distribution of the invisible gas that the light encountered on its long journey. A single quasar gives us a one-dimensional core sample, a narrow pencil beam through the cosmic web. But by observing thousands of quasars scattered across the sky, each one backlighting a different line of sight, we can slowly build up a three-dimensional map of this gaseous architecture. This technique has revealed that the vast majority of the ordinary matter in the universe does not reside in stars or galaxies, but is instead woven into this immense, hot web of intergalactic gas, tracing out the very same dark matter filaments that gravitational lensing revealed. The glittering galaxies are merely the dense knots where this cosmic gas has cooled and collapsed to form stars, the sparkling condensations on a vaster, invisible framework. This method transforms a single streak of light into a deep core sample of the cosmos. By analyzing the unique pattern of absorption lines in a quasar's spectrum, astronomers can essentially unroll a scroll that details every cloud and filament of hydrogen gas the light encountered on its multi-billion-year journey to Earth. This gives us a one-dimensional slice, a narrow but incredibly deep probe into the architecture of the universe at a specific moment in its history. It is a direct measurement of the cosmic web's condition from an era long before our solar system even existed. The real power emerges not from one quasar, but from an entire array of them. Imagine dozens of these brilliant lighthouses scattered across the sky, each one backlighting a different, narrow path through the cosmic void. By combining the data from hundreds or even thousands of these individual core samples, scientists can perform a feat of cosmic tomography. Just as a medical scan builds a three-dimensional image of the human body from many two-dimensional slices, this technique allows us to assemble a three-dimensional map of the universe's primordial gas distribution. We can begin to see the subtle outlines of the filaments and voids themselves not as they are today, but as they were when the universe was only a fraction of its current age. This is a form of cosmic archaeology, letting us look back through layers of time. Each quasar's light is a messenger from a specific epoch, and by comparing maps built from quasars of different distances, we can watch the cosmic web grow. We can see how the delicate, diffuse filaments of the early universe slowly came together, how gravity drew matter into the nodes, and how the vast voids expanded and cleared over billions of years. This time-lapse view of the largest structure in existence reveals the dynamic nature of our cosmos, showing us that the cosmic web is not a fixed sculpture but a living, evolving entity, and its history is written in the ancient light of these brilliant beacons. These digital universes are born from pure mathematics and staggering computational power. We cannot rewind our own cosmos, but we can build a new one inside a machine, starting from the same primordial conditions captured in the cosmic microwave background. Projects like Illustris TNG and EAGLE are not simple animations. They are complex virtual laboratories governed by the precise equations of physics, where dark matter, gas, stars, and black holes all interact over the entire lifespan of the universe. The goal is audacious: to witness the entire cosmic story unfold from first principles. The simulation begins with a nearly smooth, expanding universe, seeded with the tiny density fluctuations we see in the ancient light. Then the clock starts. Gravity immediately gets to work, tugging the invisible dark matter into its familiar web of filaments and halos. But this is where the story gets truly rich. Ordinary gas drawn into these dark matter wells does not behave passively. It can heat up, cool down, and eventually collapse to form stars. These stars live out their lives and then release their energy in powerful events, spreading newly forged elements back out into the void. At the centers of galaxies, supermassive black holes awaken, their intense activity pumping tremendous feedback into the surrounding gas. This cycle of creation and release is crucial. Without the powerful energy from stellar events and black holes to heat the gas and prevent it from cooling too quickly, galaxies would grow far too large, too bright, and too fast. The simulations show us that this feedback acts as a cosmic regulator, a series of carefully balanced processes that sculpt galaxies from within and dictate how matter is distributed along the cosmic web. Running a model of this complexity is one of the most demanding tasks in all of science. It requires months of calculation on the world's most powerful supercomputers, tracking the gravitational interactions of billions of particles and the fluid dynamics of cosmic gas. The final product, however, is a revelation. It is a complete virtual universe, one we can pause at any moment in its history. We can rewind to watch a specific galaxy form, or zoom out to see the large-scale structure emerge in its entirety. We can even run the simulation with slightly different rules, perhaps less dark matter or more dark energy, and see how the resulting cosmos would differ from our own. This gives us unparalleled insight, allowing us to test our theories against observation in a way that was once impossible. The stunning visual match between these simulated universes and the maps we create from telescope data is a powerful confirmation that we are beginning to understand the fundamental forces that wrote the blueprint for everything we see. For years, our cosmic accounting was deeply flawed. When scientists added up all the normal matter they could see in the nearby universe, the stars and galaxies and cold gas clouds, the total was surprisingly low. It accounted for less than half of the matter that should have been created in the Big Bang, according to the pristine record of the cosmic microwave background. This was the missing Baryon problem, a significant gap in our understanding of where ordinary matter had gone. It was as if we had a detailed manifest for a ship's cargo, but upon arrival, over half of the listed items were nowhere to be found. Where could an entire universe worth of atoms simply vanish? The answer was hiding in the most obvious place of all, the cosmic web itself. Supercomputer simulations revealed the cause. As the universe evolved, gravity did not just pull matter into filaments, it worked with immense energy. When vast rivers of gas flowing along the dark matter scaffolding met, they created colossal shock waves like sonic booms on a cosmic scale. This process heated the diffuse intergalactic medium to staggering temperatures of millions of degrees, transforming it into a searing plasma known as the warm-hot intergalactic medium. This is the universe's missing normal matter. We could not see it because this ultra-hot gas behaves differently from anything we are used to. It is far too hot to collapse and form stars, so it does not glow with the light of stellar nurseries. And it is so incredibly diffuse, a near-perfect vacuum by earthly standards, that it does not absorb light in a way our traditional telescopes could easily detect. It became a hidden component of the cosmic web, something that was theoretically present but practically invisible. The simulations showed that this warm-hot intergalactic medium contains the vast majority of the baryons in the present-day universe, effectively solving the mystery. The matter was never truly missing. It was just waiting in plain sight, woven into the superheated fabric of the web, waiting for us to develop the right tools to find it. This faint X-ray whisper is the final clue in a cosmic treasure hunt. To find the missing matter, astronomers had to stop looking for the light we can see and start searching for the glow of pure heat. The warm-hot intergalactic medium is a plasma so incredibly hot that it does not shine in visible light. It glows in high-energy X-rays. Only specialized observatories in space, like NASA Chandra and the European Space Agency's XMM Newton, can detect this faint signal. Their strategy was to aim these powerful telescopes not at brilliant galaxies, but at the seemingly empty spaces between colossal galaxy clusters. These are the intersections of the cosmic web, the places where computer simulations predicted the densest rivers of hot gas should flow. It is there, in the profound darkness between islands of light, that they have found the signature they were looking for. The evidence comes in two forms. The first is an extremely faint, diffuse glow of X-ray emission, the collective warmth from that vast ocean of hydrogen plasma. The second is even more specific. As the light from a distant X-ray source travels through a filament, the superheated gas within it absorbs very specific X-ray energies, imprinting dark lines on the spectrum that act like a chemical barcode. These lines are the fingerprint of oxygen atoms that have been stripped of most of their electrons, a state only possible in an environment of extraordinary heat. Detecting this signal is one of the most difficult tasks in modern astronomy. It is the observational equivalent of trying to hear a single, soft note played in a symphony hall during a thunderstorm. Yet, after years of careful analysis, the signal is there. This is the first direct confirmation of the warm-hot intergalactic medium, the long-sought reservoir of the universe's normal matter. We have finally located the missing atoms, and they are exactly where the cosmic web's blueprint said they would be, woven into the very fabric of the largest structure in existence. The fate of a galaxy is written in its cosmic address, a brilliant city of stars residing at the dense intersection of multiple filaments lives a life of intense pressure. The space between galaxies in these crowded clusters is not empty, but filled with a superheated plasma known as the intracluster medium. As a galaxy moves through this searing environment at incredible speeds, it experiences a constant gale force headwind. This relentless pressure acts like a cosmic blowtorch, stripping away the galaxy's vast reservoirs of cold gas, the very raw material needed to create new stars. Without this fuel, the galaxy's stellar nurseries quiet down. Its remaining stars age together, their collective light shifting to a cooler, redder hue, creating what astronomers call a red and dead galaxy, a place where star formation has been permanently stilled. Its story of growth is complete, yet just a short journey away along the dark matter filaments, a different narrative unfolds. Here, in the quieter suburbs of the cosmic web, galaxies lead more isolated lives. Far from the intense activity of the cluster center, they are connected to the universe's primordial gas supply. A slow, steady trickle of cool, fresh hydrogen flows along these invisible cosmic highways, a continuous river of potential feeding the galaxy over billions of years. This gentle, sustained accretion is the primary way a galaxy grows, adding mass not through dramatic collisions, but through a peaceful, constant inheritance from the intergalactic medium. This is the profound influence of the cosmic environment. The web is not a static sculpture of galaxies, but a dynamic circulatory system for the cosmos, a gravitational network that delivers raw materials and imposes powerful conditions. Where a galaxy finds itself on this vast map ultimately determines its destiny, shaping everything from its color and brightness to the very rhythm of its stellar life cycles. Even the smallest cosmic structures can challenge our grandest theories. This puzzle begins with the faint, dwarf galaxies that orbit giants like our own Milky Way. Our most powerful computer simulations paint a very specific picture of how these satellites should behave. They predict that small galaxies fall toward a large host over billions of years, arriving from all directions as they travel along the many dark matter filaments that connect to the central galaxy. The result should be a roughly spherical, chaotic swarm of satellites orbiting in random paths, a celestial beehive buzzing with no particular order. Yet when astronomers look at the real sky, they see something entirely different. Around our Milky Way and our neighboring galaxy Andromeda, many of these satellite galaxies are not scattered randomly. Instead, they are aligned with startling precision, arranged in vast, thin, and incredibly fragile planes. They orbit in concert like cars on a cosmic racetrack, a configuration so striking it has earned a dramatic nickname, planes of satellites. This discovery sent a ripple of concern through the world of cosmology. Such a flat, coherent structure is incredibly difficult to produce through the standard model's chaotic, filamentary accretion. It would be like dropping dozens of marbles onto a trampoline from all sides and expecting them to spontaneously arrange themselves into a single, spinning disk. The odds of this happening by random chance are vanishingly small. This leaves scientists with a profound dilemma. Are these planes of satellites simply a cosmic mirage, a statistical fluke that our local universe happens to display? Or do they point to a deeper flaw in our understanding? Perhaps dark matter behaves in a more complex way than our simple cold dark matter model allows. Maybe the process of galaxy formation involves unknown physical forces that can orchestrate these delicate dances. This ongoing mystery proves that the cosmic web is not just a story of the largest scales. Its influence cascades down, shaping the fate of individual galaxies and their companions. By meticulously mapping the local architecture of our own galactic neighborhood, we are conducting a fundamental test of the rules that govern the entire cosmos. The silent, rotating planes of these small galaxies ask a quiet but persistent question, one that challenges the very foundation of our cosmic blueprint. We stand at the threshold of a new era in cosmic cartography. The next generation of observatories is poised to transform our rough sketches of the cosmic web into a breathtaking, high-definition film. This revolution is being driven by instruments of staggering ambition, like the Dark Energy Spectroscopic Instrument, known as DESI. This project alone aims to measure the precise distances to over 30 million galaxies and quasars, building a three-dimensional map of the universe that is deeper and more detailed than anything we have ever seen before. It is a cosmic census on an unimaginable scale. They are joined by the Euclid Space Telescope, currently on its mission to chart the shape, distribution, and evolution of billions of galaxies, and the ground-based Vera C. Rubin Observatory, which will conduct the legacy survey of space and time. This survey will essentially scan the entire visible sky every few nights, creating a 10-year time-lapse movie of the cosmos and detecting billions of new objects. The combined power of these projects will do more than just add more dots to our map. They will allow us to see the cosmic web in motion. By measuring the universe's structure at different epochs, we can watch how the filaments have thickened and the voids have expanded over billions of years. This time-lapse view is the key to unlocking the universe's greatest secret, the nature of dark energy. We will see, for the first time, how this mysterious force has been pulling on the very fabric of the cosmic web, accelerating its expansion and shaping its ultimate destiny. We are moving from a single, static snapshot to a dynamic biography of the largest structure in existence. Deep within the faint whisper of the cosmic microwave background lies a fossilized echo, a relic from a time when the universe was a searing, opaque sea of primordial plasma. In that first intense moment, ordinary matter and light were locked in a constant, dynamic interplay. Gravity tried to pull the atoms together, while the immense pressure of the trapped photons pushed them steadily apart. This created a clash of titanic forces, generating powerful spherical sound waves that raced outward through the infant cosmos. These were not sound waves as we know them, but massive ripples of overdensity, expanding at over half the speed of light through the hot soup of particles. Then the universe cooled. When atoms finally formed, the fog lifted and light was set free on its long journey. At that precise instant, the sound waves stopped in their tracks. They froze, imprinting their signature onto the distribution of matter like a stamp on cosmic clay. This left a subtle but lasting pattern, a preferred distance of about 500 million light-years that became woven into the very fabric of the emerging cosmic web. We call this relic a Baryon acoustic oscillation, and it gives us something astronomers have always sought, a standard ruler. Imagine you had a measuring stick that you knew was exactly 1 meter long. If you saw it in the distance and it appeared smaller, you could calculate exactly how far away it was. The Baryon acoustic oscillation is our cosmic meter stick. We know its true size from the physics of the early universe. So when we look at the distribution of millions of galaxies in our vast maps from projects like the Dark Energy Spectroscopic Instrument, we search for this specific scale in their clustering. We measure how much this standard ruler appears to have been stretched by the expansion of space itself across billions of years. It is a direct measurement of the universe's growth, allowing us to track how the cosmic web has been shaped and extended over time. This technique provides one of the clearest and most powerful lines of evidence for the presence of dark energy. By comparing the apparent size of the Baryon acoustic oscillation ruler at different cosmic epochs, we can see the unmistakable signature of the universe's expansion accelerating, a steady, persistent force that is stretching the largest structure in existence thread by thread. This accelerating expansion is not merely pushing galaxies apart, it is actively shaping the architecture of the cosmic web itself. Dark energy acts as a counterforce to gravity's relentless pull, creating a cosmic tug of war on the grandest possible stage. While gravity works tirelessly to draw matter into filaments and clusters, dark energy stretches the very fabric of space between these structures, making it harder for new connections to form. This competition is frozen in time within the large-scale maps we create. By measuring the exact rate at which the cosmic web has grown over billions of years, we are essentially taking the universe's vital signs. The subtle imprint of Baryon acoustic oscillations gives us a fixed ruler to measure cosmic stretching. Weak gravitational lensing reveals how the distribution of mass, both seen and unseen, has evolved. And the overall clustering of galaxies shows us how densely matter has packed itself together over cosmic history. Each of these techniques tells us something unique about the strength and nature of the dark energy that opposes gravity's work. The central question is whether this mysterious force is truly constant. If dark energy is unchanging, a permanent fixture of empty space as Einstein once proposed, then the fate of the cosmos is a slow, gradual expansion into an ever-darkening quiet. Galaxies will be pulled so far apart that their light can no longer reach one another, and the cosmic web itself will gradually fade from view. But if dark energy is not constant, if its strength has varied over time, the ultimate destiny of the universe could be far more dramatic. A strengthening force could one day overwhelm even the bonds within galaxies, stars, and planets, leading to a profound transformation of the very fabric of reality. The answer is encoded in the geometry of the filaments and voids we are now so carefully mapping. Each new measurement of the cosmic web is not just a point on a chart, it is a vote for one possible future over another, a clue to the final chapter of our universe's story. To witness the construction of the cosmic web, we must journey back to its very beginnings, to a time when the universe was a simpler, darker place. The first billion years after the Big Bang were a period of profound transformation, known as the Epoch of Reionization. Before this, the cosmos was filled with a thick, neutral hydrogen fog, a featureless expanse where light could not travel far. Then, a revolution began. The very first stars and galaxies ignited, their intense ultraviolet radiation starting to clear the cosmic mist, ionizing the hydrogen and creating the transparent universe we see today. This was not a gentle dawn, but a dramatic upheaval that fundamentally changed the cosmos. It was also during this dynamic era that the first delicate threads of the cosmic web began to take shape. Guided by the unseen influence of dark matter, the primordial gas started to flow along the gravitational contours, gathering into the first filaments and pooling at the nodes where the earliest galaxies would form. Observing this foundational work is one of astronomy's greatest challenges. The light from these first structures has been traveling for over 13 billion years. The expansion of the universe has stretched that ancient light tremendously, shifting it from visible colors deep into the infrared part of the spectrum, far beyond what our eyes can see and even beyond the reach of most telescopes. This is like trying to hear a whisper from across a roaring canyon. To detect it, we need a new generation of eyes on the sky. Instruments like the James Webb Space Telescope are our time machines, engineered specifically to capture this faint, redshifted glow. Its immense mirror and sensitive infrared instruments allow it to peer back to the moment when the first stars and small dwarf galaxies began to illuminate the dark matter framework. It will search for the telltale signature of primordial hydrogen gas glowing within the infant filaments, not from starlight, but from the energy of the universe's reionization process itself. Soon, it will be joined by the Nancy Grace Roman Space Telescope, which will conduct vast surveys of the early universe, mapping the distribution of these first galaxies with unprecedented breadth. Together, they will reveal the cosmic web in its infancy, showing us the moment the universe's hidden architecture first began to emerge from the darkness, a blueprint written in the faintest light of all. The cosmic web we have mapped is a stunning achievement, but the blueprint itself is now being questioned. While the Lambda CDM model provides an incredibly accurate picture of our universe, a handful of persistent anomalies have prompted a small but determined group of physicists to ask a radical question. What if we have been misreading the cosmos all along? What if dark matter does not exist, and the force of gravity itself behaves differently on the vast scales of galaxies and beyond? This idea is known as modified Newtonian dynamics, or MOND. Its central proposal is elegantly simple. Perhaps, at the extremely low accelerations experienced in the outskirts of galaxies, gravity does not fade as quickly as Newton or Einstein predicted. This slight modification could perfectly explain why stars at the edges of spiral galaxies orbit just as fast as those near the center, an observation that first led us to propose dark matter. MOND successfully accounts for the motions within many individual galaxies without any invisible substance, yet this elegant solution faces a monumental challenge. It struggles to explain the large-scale evidence for an unseen gravitational hand, the precise patterns in the cosmic microwave background, the subtle gravitational lensing of the cosmic filaments, and the very existence of the cosmic web's immense structure all point toward a vast amount of additional mass that MOND, in its current forms, cannot easily replicate. The cosmic web, in all its grand architecture, becomes the ultimate testing ground, and here the cold dark matter model has so far held firm. Another intriguing possibility is that dark matter is not cold but warm. This is not a trivial distinction. Cold dark matter particles are thought to be slow and heavy, clumping easily from the smallest scales upward. Warm dark matter, in contrast, would be made of lighter, faster-moving particles. This slight change has a dramatic effect on the predicted shape of the cosmic web. The fast motion of these particles would have smoothed out the early universe, washing away the tiniest density fluctuations. The result would be a cosmic web with the same vast filaments and voids, but with far fewer small dwarf galaxies, as the seeds for them never properly formed. This could potentially solve the puzzling planes of satellites we see around our own galaxy, as the lack of small, early clumps might make such delicate structures more likely to form. Each of these alternatives, from modified gravity to warm dark matter, makes a distinct set of predictions for the universe's architecture. They forecast different numbers of small galaxies, different thicknesses for the cosmic filaments, and different patterns of motion within the immense voids. As our maps of the cosmos grow more detailed, we are not just drawing lines in the dark. We are conducting a fundamental test of physics itself, using the largest laboratory imaginable to ask what truly holds our universe together. Our cosmic web may be a single thread in a tapestry of unimaginable scale. Some of the most compelling theories in cosmology suggest that our entire universe, with all its filaments and voids, is just one bubble in a vast, eternally inflating multiverse. This idea emerges from our best models of cosmic inflation, that tremendous burst of expansion in the very first moments, According to this picture, inflation never truly stops everywhere at once. Instead, it ceases in isolated pockets, each one becoming a separate bubble universe, while the space between them continues to inflate eternally. Our entire observable cosmos, from the smallest galaxy to the largest filament, is contained within one of these bubbles. In this grand view, the very seeds of our cosmic web take on a new meaning. Those tiny quantum fluctuations that were stretched across the cosmos and imprinted as the blueprint for all structure, they were not predetermined. They were random, a quantum roll of the dice during the inflationary period. This means the specific pattern of our web, the exact arrangement of the Great Wall and the Boötes Void, might be a unique signature of our local bubble. The precise strength of gravity, the amount of dark matter, even the very existence of atoms as we know them, could be local bylaws, the unique physics of our cosmic neighborhood. This leads to a deeply philosophical question. Is the magnificent architecture we have mapped the one and only way a universe can be built, or is it merely one common design in an infinite ensemble of cosmic webs? Some of those other bubbles could have stronger gravity, leading to a web of far denser, more tangled filaments. Others might have weaker nuclear forces, where stars never ignite and the web remains a dark, silent structure. While this concept of a multiverse is currently beyond the reach of direct experimental proof, it represents the ultimate horizon of our exploration. It pushes our inquiry from simply understanding what we see to daring to imagine what else could be. The map of our cosmic web, in all its glorious detail, becomes more than a chart of our home. It becomes a single data point, a lone sample from a hypothetical collection of cosmic realities whose full diversity we can only begin to guess at. This vast cartographic project now extends an open invitation to anyone with an internet connection. The sheer volume of data from projects like the Dark Energy Spectroscopic Instrument is so immense that no single team of professional astronomers could ever process it all. This is where citizen science transforms the work, turning a monumental challenge into a shared global effort. Platforms like Galaxy Zoo present volunteers with real images of distant galaxies, asking a simple but profound question. What shape do you see? Is it a swirling pinwheel, a smooth oval, or a more chaotic, irregular mass? The human brain's innate ability to recognize patterns far surpasses even our most advanced algorithms when it comes to classifying these complex structures. With a simple click, a person at home becomes an active participant in cosmology, helping to tag and categorize the building blocks of the cosmic web. This collective effort does more than just speed up the work. It brings a vital human perspective to the data, allowing for the discovery of the truly unusual. A volunteer might be the first to notice a galaxy with a strange, distorted tail, evidence of a recent gravitational encounter with a neighbor. Another might spot a rare ring galaxy, a celestial smoke ring formed by a precise cosmic collision. These peculiar objects are crucial for understanding the dynamic interactions that occur along the filaments and nodes of the web, interactions that pure automation could easily overlook. Every classification adds a new annotation to our growing cosmic map, linking a galaxy's form to its specific cosmic address. This process makes discovery something everyone can be part of, reminding us that the grand architecture of the universe is not just for experts to decipher. It is a story we are all helping to read, one galaxy at a time, connecting us directly to the immense web we call home. There is an undeniable artistry to the cosmic web, a beauty that goes beyond its scientific explanation. When we look at visualizations from supercomputer simulations, we are not just seeing raw data. We are witnessing the universe's own masterpiece, a design of breathtaking complexity and elegance. Its structure echoes patterns we find everywhere in nature, from the branching network of neurons in the human brain to the sprawling, subterranean filaments of a fungal mycelium. It resembles the delicate lattice of frost on a window pane or the intricate web of a spider, all repeating a theme of branching, interconnected pathways across vastly different scales. This is not a mere coincidence. It suggests that a common logic of growth and connection, a grammar of networks, may underpin everything from the biological to the cosmic. The universe seems to favor this kind of architecture, where strength and efficiency are found in a web of delicate threads. This aesthetic resonance has not been lost on the creative spirit. Digital artists use these cosmic maps as their canvas, translating gravitational data into swirling nebulae of light and color. Composers have written symphonies inspired by the scale and structure of the filaments, translating the silent vibrations of the cosmos into sound. For philosophers and thinkers, the cosmic web serves as the ultimate metaphor for interconnectedness. It is a visual argument against isolation, a demonstration that even the most distant galaxy is linked to our own through a vast, invisible lattice. The very atoms that form our bodies were forged in the hearts of ancient stars and journeyed along these cosmic rivers to eventually find their way here. We are not just observers of this web, we are a part of its fabric. Contemplating this grand design invites a different kind of understanding, one that blends analytical thought with a deep, humbling sense of wonder. It challenges us to see the universe not only as a physical system to be decoded, but as a source of profound inspiration, a reminder that beauty and truth are often woven from the same thread. The ultimate cosmic map will not be drawn with a single color of light. It emerges from the symphony of many different messengers, each revealing a unique voice in the grand composition. We have learned to trace the brilliant cities of starlight with galaxy surveys, to feel the invisible pull of dark matter through gravitational lensing, and to sense the superheated breath of intergalactic gas with X-ray eyes. Now, the future of this cartography lies in weaving all these threads together. The next generation of observatories is being designed to work in concert, creating a multi-messenger view of the cosmos. Imagine overlaying a gravitational lensing map which shows the total mass with an X-ray map that highlights the searingly hot gas. Suddenly, you can see exactly how the invisible dark matter scaffold guides the distribution of the visible, normal matter. Add to this the subtle radio whispers of cold, neutral hydrogen, tracing the pristine raw material that has yet to join a galaxy. Finally, use the cosmic microwave background as the foundational blueprint, the original score from which all this structure evolved. When these diverse datasets are combined, they do more than just confirm one another. They interact. They reveal the dynamic relationships between the components of the web. We can watch how energy from exploding stars in a galaxy cluster heats the surrounding gas, preventing it from cooling and falling back in. We can see how the dark matter filament acting as a cosmic highway also serves as a conduit, funneling fresh gas toward hungry galaxies. This unified atlas transforms the cosmic web from a simple line drawing into a vibrant, living portrait. It shows us not just the skeleton of the universe, but its circulatory system, its energy budget, and its ongoing story of construction. This is more than a map. It is a holistic understanding of the architecture that defines everything. Our journey to map the hidden architecture of the universe has revealed a cosmos far more structured and interconnected than we ever dreamed. From the subtle influence of dark matter to the flowing currents of hot gas, we have explored the tools and theories that are slowly illuminating the cosmic web in all its grandeur. This vast network is not merely a backdrop, It is the active framework that has guided the emergence, evolution, and transformation of galaxies for billions of years, and it holds the key to understanding the nature of dark energy and the long-term story of everything. As new telescopes and surveys come online, our map will only grow richer and more detailed. The greatest mystery may be what new wonders this ever-unfolding blueprint will reveal next, inviting us all to continue looking up and wondering about the magnificent tapestry to which we belong.